Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 10th graders 2012, problem number 2. Part A. It has two parts. Part A. Solve in real numbers the following equation. 2 to the power of x equals x plus 1. And part B, functional equation. We wish to prove that if a function f satisfies this functional equation, f of x equals 2 to the power of x minus 1, for all real numbers x, then f of 0 plus f of 1 must be equal 1. So here are my hints for this problem. For part A, standard procedure, consider this function g of x equals 2 to the power of x minus 1. Differentiate it to find on which intervals is this function increasing, decreasing, and so on. And also, two solutions of this equation can be guessed easily. For part B, first, justify that f of 0 cannot be f of 1, and then show the following functional equation. 2 to the power f of x minus 1 equals f of 2 to the power of x minus 1, and use the result of part A. So give this problem a try, and I will see you in just a minute. Right, so let's start with part A. For part A, I will define function g by the formula 2 to the power of x minus 1. And notice the following things. Let's differentiate it. G prime of x equals 2 to the power of x natural log of 2 minus 1. And now it's pretty easy to see that g prime of x is greater than 0 for x is greater than binary logarithm of 1 over natural log of 2. And moreover, g prime of x is less than or 0 for x's which are less than this number. You can easily show that this is the case, what I have written. Right, which means that our function is first decreasing and then increasing. So g is decreasing strictly, decreasing on this interval minus infinity binary logarithm of 1 over natural log of 2, and g is strictly increasing on the interval binary logarithm of 1 over natural log of 2 plus infinity. Everything right? Let me take a look. Probably is. All right. And now that means that our equation g of x equals 0 has at most two solutions. It has at most two solutions. There cannot be more, because our function looks something like that. So either two solutions or 0 or 1. Alright, so can we guess two solutions? Well, notice that what is g of 0? G of 0 is 2 to the power of 0 minus 1. It's 0. And what is g of 1? It's 2 to the power of 1 minus 1 minus 1. It's also 0. So we have exactly two solutions, 0 and 1. I will write it. 2 to the power of x equals x plus 1, if and only if x is either 0 or 1. That closes part A. Part B, much more interesting. In part B, we are assuming that f of x equals 2 to the power of x minus 1, if I'm not mistaken. Right. First, notice that, of course, 2 to the power of 0 minus 1 is not the same as 2 to the power of 1 minus 1, which means that f of 0 is not the same as f of 1, and a fortiori, f of 0 cannot be f of 1. Right. And now I will take my equation once again, and I will write it in this way. First, remember that this holds for every real number x. So I can take f on both sides. This is one way of looking at it. But also, notice that I can do the following. I can, instead of x, I can put f of x instead of x. And these two expressions right here on the left-hand side are the same. So these two expressions must be the same as well. So for every real number x, we know that f of 2 to the power x minus 1 equals 2 to the power f of x minus 1. In particular, for x equals 0, if I plug in x to be 0, I have f of 0 equals 2 to the power f of 0 minus 1. And if I plug in x to be 1, I have f of 1 equals 2 to the power f of 1 minus 1. Alright, so this means that f of 0 and f of 1 are two different solutions to the equation 2 to the power of x equals x plus 1. Yes? And now we know, by result of part A, that these two solutions are 0 and 1. Since these are different, we have established that f of 0 is not equal f of 1. Since they are different, one of them must be 0 and the second one must be 1. So the order does not matter. F of 0 plus f of 1 equals 0 plus 1 equals 1, which closes the proof. And that is it. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.